Morning, everyone. My name is Felipe Garcia. I'm a member of the navigation team of Fraunhofer IPA, and I was asked to talk today about deployment examples of our IPA navigation stack that is entirely based on ROS and how we bring it into applications of AGV systems in intralogistics or unmanned material transportation systems. And in the spirit of yesterday's cloud navigation cloud sessions, I was also asked to talk about networked and cooperative navigation solutions, and a concept that we call cloud-based navigation that we've been developing over the last 3 years in terms of key navigation components. When you have a networked, interconnected mobile robot fleet, how these key components like mapping, localization, path planning can benefit from a network architecture. And I can also tell you something about the deployment of these techniques. Maybe start with a brief introduction of what we do in terms of the navigation team. We do research and development in mobile robot navigation with the whole value chain of what you need for autonomous navigation, which is perceptions, environment modeling, localization, SLAM. We have offline SLAM methods, online SLAM methods. We do motion planning and motion control. And as I said, in the context of a networked architecture, we do cooperative navigation solutions. What is today of pretty importance in terms of the session is the deployment examples. We can say that we've been providing for the last 5 years now, industrial-grade navigation solutions for AGV systems that run on a 24/7 basis and have like a reliability of over 99% in these AGV applications that you see here. And yeah, we have an automated build process, and also we use continuous integration, version control and unit testing to be safe that the system has a certain degree of reliability. So this is, I'll give you 2 examples of deployment examples that are, on the one hand, quite interesting in terms of that they run regularly in an industrial plant. The first one is sort of an AGV of Bear Automation. We have a colleague from Bear Automation here today, so if there's specific questions to the robots, I think we can discuss that. This is a system that runs at Audi. This is an omnidirectional robot by Bear Automation that runs our navigation stack and runs it, as I said, is entirely on ROS. And what they did here is they replaced a conveyor belt assembly line with a fleet of AGVs that carry these car bodies. That's an R8. And they wanted to have a flexible assembly line where the car is manufactured entirely on these AGVs. I think I have a video of it. Yeah, you can see it in action. That's an early stage of the deployment. The system has been running since 2015, I guess. And what we delivered here is we did route planning for these robots and also the base control for these omnidirectional robots. But the challenging part was localization. We do a natural landmark localization, so no artificial infrastructure. So the robot uses a laser scanner, and we do use a feature-based approach that with a Kalman filtering algorithm that tries to extract lines from sensor data, from laser scans and corners, and matches them with with offline mapped feature maps. What we also did, and that's what's interesting here, is the parts of the environment, as you may have seen in the video from the assembly line. There's a lot of movable or changeable environments. So there's trolleys on wheels that are so you don't have any structured environment. Parts of the environment are structured. There you can do a lot of feature-based localization, and parts of the environment are movable and changeable. And then we had to do an online SLAM algorithm that we also feed it into the Kalman filtering algorithm. And that worked pretty well. as long as there is enough structure in the environment. And I think Bear Automation has deployed that system to a series of fleets and also on other robots, and works pretty fine. Second example, and this is very interesting for us now because it shows all the recent capabilities of our navigation stack. Is an example from the smart transport robot at BMW, where we use long-term SLAM, reactive path planning, and also already a cloud-based control architecture. This is a robot that is also an automotive application. However, this time it's not assembling, but it's a warehouse environment, so a material warehouse, where the robot carries trolleys, material trolleys from A to B. And as I said, the interesting part here is that map management, task management, and some other stuff, monitoring, is already done in a cloud-based infrastructure. So we have down here, this is the robot layer that runs a ROS, also a ROS components, a ROS core with our IPA navigation stack. And then there's an Azure Cloud, Microsoft Azure Cloud interface. We use ROS Bridge to go from our ROS core to the IoT hub of Azure, and then we send data up into the cloud and receive data there. From the navigation point of view, what we delivered here is, of course, localization using natural landmarks without any artificial infrastructure, and online route planning and dynamic collision avoidance. Challenging is that you may see it on these images here or these pictures that there's almost no structure in this, no static structure in these environments. So there's almost everything on trolleys. So you can't work with offline maps. You got to do online mapping. Yeah, there's also a lot of dynamic obstacles. Of course, there's forklifts, workers walking around, target trains. So we got to do reactive path following. Yeah, and of course, there's the reliability of industrial grade. They say we need to have a over 99% reliable system. Okay, what we do in terms of the localization is we have a long-term SLAM concept, meaning we are continuously mapping the environment and have like different layers to distinguish between parts of the environment that are reliably stable or static and dynamic parts of the environment. And what we do, each of the robots, so this is a multi-robot setup, of course, each of the robots maps its environment, and we also share that information. So we send these maps to the cloud so that every other robot can benefit from newly detected changes in the environment. Yeah, it's here providing map updates for the cloud server. And in terms of the technique, we use a particle-based approach, a particle filter-based localization approach on different map layers. As I said, there are layers that map environment data that we consider to be rather static, and layers that are more movable, environment features that are more movable. Also, the environment is pretty large, so it's over 100,000 square meters, and so we had to deal with map management in terms of that we had low resolution grid maps, so we use grid maps that had large grids, and then we have a technique that stores in these grids the dynamics of the environment and also the contour of the objects. In terms of path planning, we use an elastic band approach. This is a classical approach that we use at IPA, and that we've extended over the last years in a way that we can do route following. So when the robot gets a global plan from the cloud, we can follow this path in the absence of obstacles. But if there is an obstacle, we can reactively avoid the obstacles. As the classical techniques, there's actually a video showing the reactiveness. And we can also do that on different kinds of robots. So the approach is feasible for omnidirectional robots, for differential drive robots. And even car-like robots, we also have outdoor applications where we have truck-like robots that do cargo handling on airports and on logistics centers that use these techniques. Okay, this is a video of the smart transport robot in action. On the left side, you see a ROS visualization of a trolley pickup, and then you see the reactive route following. And on the right side, you see a very shaky smartphone video from the venue. And you can see also here, this is not synchronized. These two videos are not synchronized. However, you can see on the right side that on the left side that the environment is very changeable. So everything, there's almost no static objects. I mean, it's temporarily static, but the next time the robot comes by, these trolleys, they were on like somewhere else. So we need to do this online mapping. Yeah, and then I think the RVIS visualization. So there's a tugger train blocking the robot. Then it picks up another trolley. And then it goes back. The robot drives, I think, 1 or 1.5 meters per second on these highways, and yeah, you see there's a lot of obstacles, and the robot has to react to them. Often it's only a slight deviation from the global path to make it. Okay. So that's an interesting project for us because it already involved cloud-based concepts. Like I said, we share maps. We receive, for example, global paths from a cloud server. This is something that we've been developing at IPA for the last 3 years, and also in the spirit of yesterday's talks, it's very interesting that so many major tech companies provide cloud-based architectures to control fleets of robots in industrial plants. Because we are not interested in providing these cloud platforms, we're interested in plugging our navigation system into these systems. Yeah, I talked on the last year's ROS-Industrial Conference here in Stuttgart a bit more about the cloud navigation concept that we have, so I will be brief about that. The idea is that we can connect with a certain infrastructure. We can connect a fleet of robots to a cloud-based server in order to benefit all the necessary components, like I said, localization, mapping, and so on, from the networked architecture. And you can see down here there's a video. It's also 2 or 3 years old already. We implemented this concept. It's not only that we have the concept in theory, so we implemented the concept so that we can integrate stationary sensors also and share navigation data among the robots. Yeah, this is basically, you can see we have a cloud server that runs a cooperative global planner and a global environment model that also holds a global SLAM server. And every robot shares its navigation data to the system and receives reliable navigation data. And you can see that the idea was to move as many parts, as many navigation components off the mobile robots to reduce hardware and software requirements locally on the robots. And then through having everything in a holistic environment model, you can also provide cooperative solutions. But as you can see, on the mobile robot level, there's still some components that run locally, so we gotta have a local motion planner on the robot, and we also gotta have a local environment model, which runs a local SLAM, as you've seen in the video. This is due to the real-time requirements, or let's say to the online requirements, so this is in the loop while the robot is driving, while these components can be computed offline. Yeah, so I'm not sure how much time I have left, because it's a rather quick talk. 4 minutes? Okay, great. How many of you have been to the lab tour yesterday? Maybe we can do a hands raise. Yeah, okay, that's great. Then you already know what I'm going to show you. This is a demo case that we showed at Automatica this year, and you've probably seen a similar demo last night at the lab tour. What you see here, using the concept that I just described, what you see here are three things. On one side, it's a cooperative local motion planning between several robots that operate in close proximity to each other. So these robots do a cooperative collision avoidance or cooperative trajectory optimization online. So these trajectories are not pre-computed, they're computed online, and then they receive each other's trajectories and do a cooperative collision avoidance. You have these situations a lot in AGV systems when you have intersections, and usually this is handled by implementing static traffic regulations where several robots need to stop to let another robot pass. And with this system you can have a continuous transition between these robots. And we tested that up until 8 robots simultaneously have these path crossing scenarios. Second thing that you see is having this networked infrastructure, we can also provide augmented reality visualization. This is done via a Unity interface on the Microsoft HoloLens. This is basically the view through a HoloLens. And then you can see laser scan data, and you can also see information or data of the robots. This is very simply here just a name, but you can imagine in terms of maintenance or deploying such systems into plants, then you could also share status information like task assignment, load, or battery, or something like that. And the third thing that you see is there are virtual robots, simulated virtual robots that also interact with a real world environment. I'm not sure if that was shown yesterday at the demo. It was okay. It seems silly to have simulated robots in these environments. However, it showed to us that it proved to us that in our projects that we are able to do a better feasibility studies and also deploying our systems. Since these robots, when you want to bring or install a new fleet of robots, it's very hard in dynamic environments to get all the robots there and then optimize your system in terms of routes. What we use is we have edge devices and small laser scanners that we put in the plant, and then we can simulate these robots on real-world data. So these robots will react to actual obstacles, and they will also react to the real mobile robots. And then we can optimize and simulate a AGV fleet on real-world data. Okay, so that will be it, I guess.
Thanks a lot for this interesting talk. We have time for 1 or 2 quick questions. Okay.
Thank you very much for your talk. Navigation is currently not in ROS-Industrial. Manipulation is, but navigation is not there yet. Do you have plans to start working on making navigation industrial grade and open source?
Yeah, okay, you mean open source. I was waiting for that. Okay. The thing is, we try to contribute as much as we can to the open source parts that we use. Of course, we use most of the navigation core parts like MoveBase or other communication stuff. And we have regular pull requests to the upstream repos of ROS from our team. However, the navigation systems that we sell to our customers, we cannot put them open source. I mean, there is an argument to do it, but at the moment this is not a plan.
Okay, maybe one last quick question. No? Okay, then let's thank the speaker again.